Hello students, it's Kailash. In this video session, I'll be teaching you how to find electric field at a point due to continuous charge distribution. And in the topic, it is common for both 12th standard samacheer syllabus and 12th standard CBSE students. 12th standard samacheer syllabus, this topic will come under lesson number 1, electrostatics. இதே 12th standard CBSE syllabus it comes in lesson number 1 again, but titled as electric charges and fields. So it's a common topic for both samacheer as well as CBSE students. So rendu perume idha watch pannalam. So how to find electric field at a point due to continuous charge distribution. Now you would have studied how to find electric field at a point due to a discrete charge, adavadhu point charge. And you would have arrived at a formula E vector is equal to 1 by 4 pi epsilon naught into Q divided by R square into R cap, where 1 by 4 pi epsilon naught is a constant and Q is a source charge and R is the distance of the reference point from the source charge, and R cap is a unit vector which is directed from the charge to the reference point. And in the formula, continuous charge distribution நம்ம employ பண்ண முடியாது. So in the formula we use panni, we can find electric field at a point only due to point charges. So the above formula is applicable only for a point charge or a discrete charge. Point charges are otherwise called as discrete charges. And of course, in our earlier video session, discrete charges na enna, continuous charge distribution na enna, and macroscopic charges na enna, why law of quantization of charges is ignored when dealing with large scale charges. இதெல்லாம் நம்ம என்னோட earlier video sessionல நீங்க பார்த்திருக்கலாம். பார்க்காதவங்க தயவு செய்து அதை பாருங்க. Okay. And so இந்த ஃபார்முலாவை டைரக்டா கண்டினியூஸ் சார்ஜ் டிஸ்ட்ரிபியூஷனுக்கு நம்ம அப்ளை பண்ணி ரிசல்ட் கண்டுபிடிக்க முடியாது. எலக்ட்ரிக் ஃபீல்டுக்கு ஆன்சர் கண்டுபிடிக்க முடியாது. இந்த ஃபார்முலாவோட I have to use integration technique to get the result. So integration technique has to be incorporated along with the above formula to determine electric field at a point due to continuous charge distribution. So how to do that? So that's what we are going to see in this video session. Okay. Now we have a small revision in continuous charge distribution. Continuous charge distribution is the one in which the charges are distributed or packed very close to each other, such that identifying individual charges is not possible. So charges don't appear as discrete, they appear as continuous. So whenever they are tightly or closely packed. Say, for example, I have a body. Now let me distribute charges on the surface of the body. If you look at the charges, they are tightly packed. They are distributed in a continuous manner rather than discrete manner. So continuous charge distribution is the one in which the charges are distributed or packed so tightly such that identifying individual or discrete charges is not possible. Okay. Now we will analyze 3 steps in determining electric field due to continuous charge distribution. Okay. Now let me consider I have a body here which is distributed with the charges in a continuous manner. So we have a continuous charge distribution of charges over this body. Now to find electric field at a reference point, we have to, first step, we have to imagine a continuous charge distribution to be a collection of number of infinitesimal identical discrete charges or point charges, each of magnitude dq. Infinitesimal means very small, nearly equal to 0. So நம்ம என்ன பண்ணணும்னா இந்த continuous charge distribution இருக்கு இல்லையா, அதை we have to imagine it, we have to assume it to be a collection of a large number of incredibly large number of infinitesimal identical point charges dq. See, I've drawn few discrete charges here. So you'll be having millions and millions of such discrete charges in the case of a continuous charge distribution. Just like a straight line is composed of several dots which are closely packed with each other, a continuous charge distribution is a collection of a number of infinitesimal identical point charges, each of magnitude dq. Infinitesimal charge means a magnitude of charge dq will be very close to 0. It's not actually equal to 0. It will be very close to 0. Now, each and every discrete infinitesimal charge here, the one what you see in the red color dots, okay, are called charge elements. I'm going to call each and every dot, a discrete charges here as charge element. So once a charge element is indicated here, okay, right. Now, second step, at the reference point, what we have chosen, find electric field due to one such charge element. So we'll be having millions of charge elements over here. அதுல ஏதாவது ஒரு சார்ஜ் எலிமெண்ட்டை வச்சுட்டு எலக்ட்ரிக் ஃபீல்ட் அட் த ரெஃபரன்ஸ் பாயிண்ட் நம்ம கண்டுபிடிக்கணும். அது ஸ்டெப் 2. ஸோ ஸ்டெப் 3, ஸ்டெப் 2ல கிடைக்கிற ரிசல்ட்டை இன்டகிரேட் பண்ணா I'll be getting electric field due to the entire charged body. அப்போ கண்டினியூஸ் சார்ஜ் டிஸ்ட்ரிபியூஷனுக்கு எலக்ட்ரிக் ஃபீல்டு ஒரு ரெஃபரன்ஸ் பாயிண்ட்ல கண்டுபிடிக்கணும்னா ஸ்டெப் 1, இமேஜின் the continuous charge distribution is a collection of large number of infinitesimal identical discrete or point charges each of magnitude dq. So you just choose one charge element, one such identical point charge. அந்த ஒரு பாயிண்ட் சார்ஜ், ஒரு சார்ஜ் எலிமெண்ட்டுக்கு எலக்ட்ரிக் ஃபீல்ட் என்ன வித் ரெஸ்பெக்ட் டு தட் ஒன் சார்ஜ் எலிமெண்ட் ரெஃபரன்ஸ் பாயிண்ட்ல எலக்ட்ரிக் ஃபீல்ட் என்னங்கிறத ஸ்டெப் 2ல கண்டுபிடிங்க. ஸ்டெப் 2ல கிடைச்ச ரிசல்ட்டை இன்டகிரேட் பண்ணோம்னா நமக்கு electric field due to continuous charge distribution kadachidum. So that is what we are going to do. Now, electric field due to continuous charge distribution will arrive at a generalized formula for electric field. So step 1, let me imagine this continuous charge distribution to be collection of number of infinitesimal point charges. Now first let me choose a reference point. Let P be the reference point. Here I'm supposed to find electric field due to this entire charged body, which is having a continuous charge distribution nature. Now let me choose one charge element, an infinitesimal charged, infinitesimal point charge, dq. Now let me find electric field at the reference point P due to this point charge. Okay. Firstly, let R be the distance of the reference point from the charge element. And let r cap be the unit vector which is directed from the charge element which is going to act as a point charge here. So let r cap be the unit vector directed from the charge element towards the reference point. So electric field at P due to dq. Since dq is a point charge, I can very well use the point charge formula what I showed you in the first slide of this video session. So electric field at the reference point P is given by 1 by 4 pi epsilon naught into, here the source charge is dq, the magnitude of the source charge is dq. So dq over distance of the reference point is r, so r square into r cap, where r cap is the unit vector directed from the point charge to the reference point. And since this is the electric field due to a very small charge, infinitesimal charge, the value of electric field is also going to be infinitesimal charge, infinitesimal electric field in fact. So since the point charge involved here is infinitesimal charge, the electric field at the reference point P due to this infinitesimal charge will also be very small. So that's why instead of E vector, I have taken it as dE vector. So dE vector means infinitesimal electric field. So this is the electric field due to one charge element. Now, step 3 in the earlier slide told us we have to integrate the result of step 2. So in the step 2 la kadacha in the result integrate panna, I'll be getting electric field due to the entire charged body. So electric field at P due to the entire charged body is obtained by integrating this. Now you know 1 by 4 pi epsilon naught is a constant, so I'm taking it out of the integral symbol. So hence I will have E vector electric field due to the entire charged body. So integrating both sides, integral dE vector will give me E vector, and right hand side I have 1 by 4 pi epsilon naught outside the integral, and inside the integral I have dq by r square into r cap. So don't forget the formula. So this is the generalized formula to find electric field at a reference point due to continuous charge distribution. Okay. Now there are 3 types of continuous charge distribution. What are they? Number 1, linear charge distribution. Number 2, surface charge distribution. And number 3, volume charge distribution. So first we shall discuss what are linear charge distribution, surface charge distribution, and volume charge distribution, and then we will go into electric field determination. Okay. Linear charge distribution. Linear அப்படினா straight line அப்படின்னு அர்த்தம். So whenever charges are distributed on a body so that it occupies a straight line. So whenever charges are distributed over a straight line on a body, then I'm going to call it as linear charge distribution. So if the charges are distributed continuously along a straight line, then such type of distribution is called linear charge distribution. You can see I'm distributing charges on a body, and you can see it forms a straight line. So it's a linear charge distribution. I can just give you an example. So whenever I distribute charges on a thin wire, it will have linear charge distribution character. So charges distributed on the surface of a thin wire is an excellent example for linear charge distribution. Okay. Now, whenever we are dealing with linear charge distribution, you should be aware of a quantity, linear charge density, denoted by lambda. So what is this linear charge density? Linear charge density is defined as charge per unit length. That is, quantity of charge occupying 1 meter length of the line. 1 meter is otherwise called unit length. So 1 meter length of the line la எவ்வளவு charges, quantity of charges occupy பண்ணுதோ அதை we call it as linear charge density. Suppose if I have a linear charge distribution like this, let Q be the total charge distributed over the length L. So the length of the alignment of the charges is L, and the total charge over this entire alignment of length L is Q. Let us imagine. Now to find linear charge density, I need to find amount of charge in 1 meter length. So here we have Q coulomb of charge distributed over a length L. Therefore, amount of charge distributed over a length 1 meter is obtained by finding the ratio of Q to L. So Q by L will give me quantity of charge present per unit length. Therefore, lambda is equal to Q by L. So this is the formula to find linear charge density. Now let us find the unit of linear charge density. Unit of charge, we have a charge in the numerator. So unit of charge is coulomb, and that of length is meter. So let me take meter to the numerator. So I end up with coulomb meter to the power minus 1. So the unit of linear charge density is coulomb per meter, or I can write it as coulomb meter to the power minus 1. So I hope you would have understood what is linear charge distribution and linear charge density. Now we will go into how to find electric field during linear charge distribution. So electric field at a point due to linear charge distribution. You know, linear charge distribution is a continuous charge distribution type. So how to find electric field due to linear charge distribution? Let me consider a thin wire. The charges are uniformly distributed on the wire. You can see the charges form a straight line. So it's a linear charge distribution. Electric field during continuous charge distribution கண்டுபிடிக்கிறதுக்கு 3 ஸ்டெப் நான் ஃபாலோ பண்ணணும்னு சொன்னேன். முதல்ல ஒரு சார்ஜ் எலிமெண்ட் நம்ம சூஸ் பண்ணிக்கலாம். ஒரு இன்ஃபைனிட்டெசிமல் பாயிண்ட் சார்ஜை இந்த கண்டக்டர்ல ஏதோ ஒரு இடத்துல நம்ம செலக்ட் பண்ணிக்குவோம். Before that, let lambda be the linear charge density of the wire. So you can see I have chosen a charge element, an infinitesimal charge whose magnitude is dq and whose length is dl. So the length of this charge element is dl, and the quantity of charge occupied by this particular portion is dq. Is it clear? Now first, let me find linear charge density with respect to the charge element. How to do that? You know, linear charge density is given by charge divided by length. Here, the charge element carries a charge dq and its length is dl. Therefore, I can write lambda as dq by dl. But before that, let me choose a reference point P, which is at a distance of r from the charge element. And let r cap be the unit vector drawn from the charge element to the reference point. Here, the charge element is going to act as a point charge. Okay. Now, lambda is equal to dq by dl. From this, let me find what is dq just by cross multiplying. So this implies dq is equal to lambda times dl. Okay. We know that electric field at the point P due to the charged body. So in the earlier slide, we 2 slides earlier, so we arrived at a generalized formula for electric field due to continuous charge distribution, isn't it? So I'm going to use that formula. So we know that E vector is equal to 1 by 4 pi epsilon naught into integral dq divided by r square into r cap. அதுல dq ஓட வேல்யூ நம்ம இங்க கண்டுபிடிச்சிருக்கோம் பாருங்க. dq க்கு ஒரு எக்ஸ்பிரஷன் கண்டுபிடிச்சிருக்கோம் பாருங்க, lambda into dl. அதை இங்க நம்ம சப்ஸ்டிடியூட் பண்ணோம்னா I will get the expression for electric field due to linear charge distribution. So substitute lambda into dl instead of dq over here. So thus, this is the formula to find out electric field at the reference point P due to linear charge distribution. Right. Now let us go to surface charge distribution. You know, there are three types of continuous charge distribution: linear charge distribution, surface charge distribution, and volume charge distribution. Adala linear charge distribution is over, and surface charge distribution முதல்ல பார்ப்போம். அதுக்கப்புறமா எப்படி surface charge distributionல electric field கண்டுபிடிக்கிறது அப்படிங்கறத பார்ப்போம். Now, whenever the charges are distributed continuously over the surface area of a body, so whenever I distribute charges on a body, and if the charges tend to occupy the surface area of the body over which we are distributing it, then such type of distribution is called surface charge distribution. So linear charge distribution, the charges should align in a straight line. Surface charge distribution, the charges should occupy the surface area of a body over which it is getting distributed. Now let me consider a body. If the charges are distributed over the entire surface area of the body, then I'm going to call such a type of distribution as surface charge distribution, right? Once when you are dealing with surface charge distribution, you should be aware of surface charge density, a quantity surface charge density denoted by sigma, just like linear charge density. Now, what is surface charge density? Surface charge density is defined as charge per unit area. So if it is linear charge density, it's charge per unit length. If it is surface charge density, charge per unit area, or in other words, quantity of charge occupying 1 meter square area. 1 meter square area, we call it as unit area of a body. Now let me consider charges which are distributed over an area A. In the area A la distribute ஆயிருக்கக்கூடிய total charge எவ்வளவு அப்படின்னா Q imagine பண்ணிக்கலாம். So let us consider Q coulomb of charges are getting distributed over the area A of a body. Therefore, let me find quantity of charge per unit area. So how much charge is getting distributed over 1 square meter area? அது எப்படி கண்டுபிடிக்கிறது? Q charge area வால divide பண்ணா I will end up with quantity of charge occupying unit area of this particular body. Now, as per the definition, I'm going to call charge per unit area as surface charge density. So sigma is equal to Q by A. So this is the expression to find surface charge density. Now let us find the unit of sigma. That is surface charge density. We have charge in the numerator. So coulomb per, we have area in the denominator. So coulomb per meter square, or if I take meter square to the numerator, I end up with coulomb meter to the power minus 1. So its unit is coulomb meter to the power minus 1. Minus 2, in fact, I'm sorry, coulomb meter to the power minus 2. And surface charge density is a scalar quantity. Just like surface charge density, linear charge density too is a scalar quantity. Right. Now let us find the electric field at a reference point due to surface charge distribution. The diagram we have a sheet. The charges are occupying the entire surface area of the body, isn't it? Right? Let sigma be the surface charge density. Let me imagine sigma to be the surface charge density. Now let me choose a charge element, an infinitesimal point charge, a discrete charge, whose magnitude is dq. So let me consider a small portion of the sheet where dq coulomb of charges are concentrated over the area dA, in the portion of the area dA. Okay. Now let me choose a reference point P, which is at a distance of r from the charge element. Let r cap be the unit vector directed from the charge element to the reference point. So here the charge element is going to act as a discrete charge or a point charge. Now let me find surface charge density sigma with respect to the charge element. How much charge is occupied by the charge element? dq. What is the area of the charge element? dA. Therefore, the expression for sigma with respect to the charge element will be sigma equals to dq divided by dA. From this, let me find what is dq. Therefore, dq is equal to sigma times dA. Just cross multiply, you get this expression. Now we know that electric field at a point P due to the entire charged body, the generalized formula. E vector is equal to 1 by 4 pi epsilon naught into integral dq divided by r square into r cap. So we have already arrived at an expression for dq here. So instead of dq, you substitute sigma times dA. You will get the answer for expression for electric field due to surface charge distribution. So E vector is equal to the constant K 1 by 4 pi epsilon naught times integral sigma dA divided by r square into r cap. So I hope you would have understood how to find electric field during linear charge distribution and surface charge distribution. Now lastly, volume charge distribution. If the charges are distributed continuously to spread over the volume of a body, the space within the body. So ஒரு hollow spaceல ஒரு பாடிக்கு உள்ள இருக்கக்கூடிய hollow spaceோட volume முழுவதையும் charges occupy பண்ணிச்சுனா, then we are going to call it as volume charge distribution. So if the charges tend to occupy the space within a body, the volume of a body, then such type of distribution is called volume charge distribution. For example, let me consider a hollow cylinder and a hollow cube. The inner space, the charges are occupying the inner volume of the cylinder. And here it's the inner volume of the cube. So since the charges are getting distributed over the volume of the body, I'm going to call such type of distribution as volume charge distribution. Now, once when we are dealing with volume charge distribution, you should be aware of volume charge density denoted by the symbol rho. Okay, rho. Now, what is this volume charge density? It is defined as charge per unit volume or quantity of charge occupying 1 meter cube volume of a body. 1 meter cube is otherwise called as unit volume. So, ஒரு objectோட 1 meter cube volume எவ்வளவு quantity of charge occupy பண்ணுதோ அததான் we call it as volume charge density. Now, let me consider a cube whose volume is V. The quantity of charge occupying the volume V is Q. To find volume charge density, I have to find the quantity of charge per unit volume. So thus Q over V will give me amount of charge present per unit volume, which as per the definition is referred to as volume charge density. So rho equals to Q divided by V. Now let us find the unit of volume charge density. We have a charge in the numerator, so coulomb, and volume in the denominator, so meter cube. So unit of volume charge density will be coulombs per meter cube or coulomb meter to the power minus 3. And of course, it's a scalar quantity. Okay. Now let us go to the next slide, wherein we are going to see how to find electric field due to volume charge distribution. Now let me consider a cylinder wherein the charges are distributed over the volume. So it's a volume charge distribution. So step 1. Let dq be the quantity of charge focused over the charge element whose volume is dV. So I'm choosing a small elementary portion of the cylinder. So if that particular small elementary portion of the cylinder contains an infinitesimal charge dq, then I'm going to call it as a point charge, or it is going to act as a point charge or a discrete charge, which otherwise I'm going to call it as charge element. So let me choose a charge element over here, which carries a charge dq and whose volume is dV. Now let me choose the reference point P, which is at a distance of r from the charge element. Let r cap be the unit vector, which is directed from the point charge, it's dq here, to the reference point P. Now let me find volume charge density with respect to the charge element. How much charge is present in the charge element? It is dq. What is its volume? dV. Therefore, dq by dV is going to give me volume charge density. Now, on cross multiplying, I get dq to be equal to rho times dV. Now we know electric field at the point P due to this charge element. The charge element acts as a point charge here. Will be 1 by 4, the generalized formula, 1 by 4 pi epsilon naught into dq by r square into r cap. Integrating that, I'll be getting electric field due to the entire charge of the body. Therefore, electric field at the point P due to the entire charge of the body is obtained by 1 by 4 pi epsilon naught integral dq over r square into r cap. Substituting rho times dV instead of dq over here, I get the formula to find electric field during volume charge distribution. So E vector equals 1 by 4 pi epsilon naught into integral rho dV divided by r square into r cap. So that's all about electric field due to continuous charge distribution. I hope you would have understood. So thanks a lot. Meet you in the next video session. Until then, it's Kailash signing off. Thank you.